So we'll start with two more talks that will describe analysis of new simulations, in particular baseline V2 compared to the old one. And then we will continue with science collaborations report. And all these presentations are already linked to our webpage for the agenda of this workshop, including Google Slides from science collaborations. So we start with Lynne. Lynne, it's yours.
All right. So 15 minutes to go through the changes from baseline 1.7.1 to 2.0. That's so first of all, the changes from here, I just talk about a comparison to the baseline 1.7.1. Basically, there's changes with the footprint, as we've already talked about, but some other details are that the 1.7.1 baseline was created with LSST SIMS code, which uses the seeing cloud and sky brightness, etc., from LSST SIMS. The baseline 2.0 is created with RibbonSim. Now, RibbonSim is a repackaging of LSST SIMS, and Peter's going to talk more about that later. But basically, this is actually the same data and the same code, but now it's in RibbonSim. There's a small change on the start date from 1.7.1 to 2.0. We advanced it a year. Listening earlier, I realized we will probably want to do some simulations starting in April 1 of 2024, just to check if that makes any significant differences. The total number of visits is about the same. The visit pattern is similar, like the old 1.7.1 simulation used 2 by 15 second visits and UGRI, Z, and Y. And currently we're using in 2.0, 2 by 15 second visits in GRI, Z, but then 30 second visits in U-band. The visit pairs for 1.7.1 were in mixed filters with a 22-minute separation. And in the current simulation 2.0, we still have mixed filters. We lengthened that pair separation slightly to 33 minutes. Some other things that are the same between the old simulation 1.7.1 and 2.0 are that the U-band swaps with Z-band, because we can only hold 5 filters in the carousel, at around plus or minus 6 days around new moon. Another thing that's the same as the sky tessellation is randomly visited each night, but not within a night. And that there are 5 deep drilling fields, which are allocated about 5% of the total survey time. The general idea of the footprint is maintained in that we have a wide, fast, deep area, and this is defined as areas which get about 825 visits per pointing. And then we have mini survey areas which have a few hundreds of visits per pointing, and then the 5 deep drilling fields. So on the left here, you see the 1.7.1 baseline, and on the right is the 2.0 baseline. So the general gist of the footprint is the same, but there are some differences. So as we talked about earlier, the wide, fast, deep area has been shifted. Let's see, oh, I didn't have the footprint in the next one, so I'll just explain it here. The wide, fast, deep area has been shifted so that we have more area on the sky that is in low dust extinction regions. And then we add the galactic bulge and the Magellanic Clouds to what is now considered the wide, fast, deep area, so that basically we're focusing this wide, fast, deep area on regions that need more visits and not including as much of the dusty plain in this wide, fast, deep area. So this ends up shifting a little bit more area into that few hundreds of visits per pointing on the sky and increasing the overall total footprint slightly as a result. So the result upshot of that is that we end up with slightly fewer visits per pointing in most regions, but it's only slightly. If you go and compare the amount of area between baseline 1.7.1 and 2.0 that gets 750 visits per pointing, it's basically the same. So this is the what we would call wide, fast, deep area. It's the same or slightly more. We do get slightly less area that's covered to 825 visits per pointing, and this is due to just unevenness of coverage and edge effects where you have roll-offs near the edge, for example, from dithering. But the dust-free area, so this is the not really dust-free, but low dust area, increases by about 10% due to this shift in the wide, fast, deep location. The median visits per pointing in the wide, fast, deep is very similar, slightly less. When you look at the mini surveys, so this is the North Ecliptic Spur and the non-bulge galactic plane, you can see that there's a little bit of shift here. In particular, notice that the area for the NES increases, and the area for that dusty plane increases by a lot, because now we have this part of the sky is now part of the dusty plane. And so this reshuffles some of the visits or the number of visits per pointing in these areas. The other change is that we added 2 regions, this is 4 separate bands, rolling cadence in that low dust, wide, fast, deep into the baseline. The rolling cadence starts at year 1.5 and ends at year 8.5. This is actually 6 seasons of rolling for non-rolling. So it's not rolling cadence for the whole time, but for a large part of it. And what you see here are 2 movies. On the left is the number of visits per pointing. And so this is cumulative over the lifetime of the survey. And on the right is the co-added depth, including dust extinction. So one thing that you notice is that as this goes through, at the start of the survey, the sky is uniformly covered, because that's how we're starting the survey. And at the end of the survey, the sky is uniformly covered. In between, so now it's starting up the rolling, you can see these stripes moving back and forth. And it's not super obvious just because of the intervals that I chose to make these plots at. These are sort of on half-year intervals. So you do get an uneven coverage as a result in the number of visits. What I think is interesting to note is that this doesn't show up quite as strongly in the co-added depth, because it does show up quite strongly at the start, but because of the way that co-added depth increases over time, after the first few years of rolling cadence, so this is year 2.5, it's quite strong. At 3 by 4, the variation in co-added depth across the sky is much less, just because of the fact that how co-added depth adds up over time. Anyway, rolling cadence is a big topic that we've added into the baseline. We are looking into this in depth. I'm setting up a rolling cadence task force. If you're interested in that, please reach out and send me an email. I'm trying to set that up right now. I have a list of names. Basically, these people are very interested in rolling cadence, would like to make sure they have input, and are kind of on the hook for making sure that we are considering all of the aspects that we need to. Other tweaks to the 2.0 baseline. Now we have twilight visits occur in pairs with a 15-minute separation. The galactic bulge and Magellanic clouds do get wide, fast, deep level visits, but they have a slightly different filter distribution, which you can see more clearly in this plot of the number of visits per filter. So there's slightly more visits in G band, slightly less visits in U band in the galactic bulge. And then there's some other differences internal to the code. Well, I wanted to pop up a brief overview of the metrics. I know that this is a lot of numbers in a small amount of space. What you might notice though, so in each of these, this is the 1.7 column first of the metric value, and then the 2.0 value. And then the ratio is the ratio, but it's normalized if the metric is intended to to, like, for example, the parallax error, as it gets a larger number, that's worse. And so the ratio takes that into account. And so it's flipped the correct order. Now, this is from 1.7.1 to 2.0. We think we've improved things in general. So notice, for example, that for cosmology metrics, the effective survey area increased by about 10%. And then there's a corresponding increase in a lot of the desk static science metrics that basically scale with the effective survey area. For the transition variable science, we see if you classify supernova 1A detection in this group, you see that the number of supernova detected increases by about 30%. And this is due to the addition of the rolling cadence. So it's improving the spacing between visits. We also see an increase in the microlensing on short time scales. And this is partly because there's more coverage of the bulge, and also because as there's more coverage of the bulge, the time scale of the visits increases. So this is sort of a dual benefit here. What do we see that might be bad? Well, the median parallax error got a little bit worse, and so did the proper motion error. And also for faint objects in the solar system, we are noticing that the completeness for these objects decreases slightly. And if you look at the total number of NEOs, particularly that are down to very small sizes, you see a similar sort of drop, slight drop in the number of objects. And I think we maybe don't fully understand what the cause of that is, because it's likely something about how we're surveying the sky and how deep the visits are going in a particular chunk of time, and the coverage of various parts of the sky. So I think we probably need to dig into that a little bit more, but it's something to consider. Overall, though, the metrics do look good for the new baseline, and we think that this is an overall improvement. That is my time. I'm just going to check the chat and see if we had. Oh, yeah, okay. So question about what is swapping. Yeah, sorry. So for these metrics, more than one is good, less than one is bad.
I'm looking at your median quoted M5I band in the top right corner of the slides. It would make more sense to compare, to look at the difference of the limiting depth rather than ratio. If you ratio, you could look at the effective observing time. You translate magnitude to effective observing time.
Yeah, you're right. And actually, usually when we do these metrics in the full series of plots that we have, we actually do account for that properly. But I made this and I overlooked that one. You're right.
We are right on time. Are there more questions for Lynne?
What is the reason for the very, very significant microlensing 1 to 10 days increase?
So that's because of the distribution of the microlensing events on the sky. They're very focused towards the galactic bulge.
So that's footprint.
Yeah, it's footprint, but also yeah, it's footprint in the fact that there's many more visits in that area, so that the time scale between visits in this area where you now have more visits is good.
Thank you.
Oh, sorry. I guess I did have a little summary of just some of this overarching differences. And as Peter went through earlier, there's these in the V2.0 simulations, there are some retro simulations which you can compare against these older simulations. So the retro baseline is the one that basically should be exactly the same as baseline NX2 V1.7.1. except created with ribbon sims. So there may be some very small differences. It won't be exactly identical, but statistically the same. And then the retro foot is like the 1.7.1 configuration, but updated with some of the new features. So you can kind of step through if you're not sure which part of this, whether it's the rolling cadence or whether it's the footprint, whether it's something like the U-band visits that your metric is changing with, you can step through these retro simulations to see where the big change is coming from.
We have one raised hand and we have question from Meg too on Slack. So let's invite Graham Smith to ask his question first.
Hopefully a quick question. On the previous slide, is the kilonova metric relating to TOO, graph wave follow-up, or just detecting them blind in wide fast deep?
Yeah, this is just detecting them blind in the wide fast deep.
Thanks.
And Fed made some comments that maybe the supernova 1A metric that here I put in the TVS group and previously I had put in the cosmology group might be a metric that is more aimed at supernova 1A from the point of view of cosmology. And that's fair. I moved it here because I thought we include the strong lensing supernova in the TVS set of metrics. It may be that we are sort of just need to swap where we're considering that. Mike's question on Slack is kind of a bigger question, and I will take that up with her on Slack, I think.
Okay, good idea. Let's continue with Peter. You need to stop sharing, Lynn. Okay, and then we'll go with Peter.
Okay, I'll address John's Slack comment. He pointed out that parallaxes have taken a hit, and I just wanted to mention that that's a little bit deceptive. The parallax precision goes down about 5%. Part of that is because the wide fast deep area increased. So it's not just that we're doing worse, we're getting more area at slightly lower precision. So it's not all bad. All right, so let me get to sharing. And share. There we go. Okay, so I'm going to talk about metric trends. This will probably go pretty quick, so we'll have lots of time for discussion of things if people want to chat about them. So just a reminder, you can go look at all the metrics yourself at this link that we've put up a couple times now. So there's the whole list of 127 runs. I'm going to focus on kind of my 3 favorite metrics for looking at things, just because if we did all of them, it would be overwhelming. So as Lynn's already pointed out, we've got our supernova metric that was contributed by Desk. It's the number of supernovae at each helium pixel. And so the way this metric's working is it goes to each helium pixel, finds the visits that overlap that spot, does a Monte Carlo simulation there, and given the area of that helium pixel, and says how many supernova does it expect to successfully observe and recover, and at what redshift. And our baseline is currently saying we get about, if we sum up over everything, we get around 25,000 over the 10 years. We need to double check with Desk to make sure that's right. There might be an inside bug in there, but for relative comparisons, it looks good. We've got our proper motion uncertainty. And so this is, in this metric, we're taking a 20.5 magnitude star, moving it to every single helium pixel, and then using the observing conditions to compute what would the uncertainty on a proper motion fit be. And the baseline median across everything is 0.2 milliarc seconds per year. And I should point out, this is the target value in the science requirement document. So we don't have a lot of wiggle room for damaging proper motion if we change the survey strategy. And in all the plots, I'll plot the inverse of this, just so that bigger is better, but smaller precision, of course, is better. And then we've got our micro lensing events, like Fed was asking. They're very concentrated on the bulge, and you can also see the LMC and SMC pop up there. And so this is very sensitive to footprint. So as long as we're covering the bulge, we recover most of these, especially the fast ones. The long ones last long enough that we almost get them no matter what. And so this metric works by generating 10,000 fast microlensing events and then checking each one individually to see which ones pass a detection criteria. And our baseline survey says we detect 47% of them because, you know, the bulge is up about half the time. And so we get about half of them. My aside, so these are all running very different ways to compute their science cases, but all of them rely very heavily on the 5 sigma depth column from our simulation output. And so none of them have to use a spatial cut, a filter cut, a wide fast deep only cut, an exposure time cut, none of that. As long as you rely on 5 sigma depth and are computing you know, some sort of signal to noise, you don't need these additional cuts. So I'm encouraging everyone, while you're writing metrics, use the 5 sigma depth, because if you don't, it's almost guaranteed that there'll be some weird edge case observing strategy that breaks your metric and makes it give strange results. You'll rank in a strategy very highly when it's actually not helping your science if you're not using proper signal to noise calculations. And these are 3 great metrics to use to bootstrap. If you know, if you have a different type of object, you can just swap in your object and use the same Monte Carlo machinery to do your own kind of object. Okay, so I'll show a lot of trends for some of our different families. This one is varying the north ecliptic spur strength, and so I'm going from, you know, kind of 1% of what we're doing now up to, you know, the same number of visits as the wide fast deep. Dashed line is the baseline, and so and you can see the supernovas show a pretty strong trend where if we give more time to wide fast deep, the supernova like it. If we put lots of time into the NES, the supernovas suffer. Everything else is kind of plus or minus 5%. And so, and again, I apologize. The supernova metrics are running right now. They are the most processor intensive things to run. So we should see a trend of, you know, of solar system objects trending up, and this way, you know, crossing at the baseline value around there. And so this should give the SCOC a good way to balance how much solar system science do we balance against cosmology science. But there's a nice trend there. Same thing for the galactic plane, going from a tiny bit of galactic plane to full coverage of the galactic plane. And so now you can see if we treat the entire galactic plane like wide fast deep, we really do hurt a lot of cosmology science. And again, the microlensing doesn't vary at all because that's focused on the bulge. And so this doesn't change the bulge observations at all. So that's unaffected. And then our proper motion takes a tiny dip, but again, we would be getting more area with good proper motions. So that might be kind of an illusionary. And so we definitely need some sort of metric that will trend up here. We don't really have a science metric that says, here's all the good science I'm going to get out of the dusty plane. So we need a metric that will balance this out. Otherwise, we can just say, oh, we can cut the galactic plane a lot and get more science. There's nothing arguing for more right now. But I suspect there are a lot of stars there. There are a lot of objects. There should be some science cases that can argue here. Rolling is great because it jumps around all over the place, and there's lots of potential trade-offs to be done with different rollings. So in general, supernovae like rolling early and rolling longer and rolling at larger strengths. Being too aggressive with rolling in the bulge kills the fast microlensing. So I think yeah, rolling bulge 6, this is where we divide the bulge into 6 different bands and roll. And so that means some seasons we're just not observing much of the bulge, and so we lose a lot of microlensing events. And then again, 6-band rolling in the wide fast deep hurts our proper motion quite a bit. We're not getting a long enough baseline for proper motion measurements if we get too aggressive with the rolling in the wide fast deep, and so that could be an issue. But it does help supernovae. So and in general, you see these ones that say 0.5, that's weaker strength rolling, and so that doesn't give us much of a boost on the supernova. We need kind of the 80 to 90% rolling strength to get the boost on the supernovae. So, and again, we can decouple the rolling, and we haven't really looked at rolling in the dusty bulge or the NES. And so if people are interested in doing that, these regions are decoupleable, so we can roll different areas different ways if we want to. Long gaps, this is where we were looking for that kind of 4 to 7 hour timescales. And there we go. I gotta move my Zoom window so I can actually see my own plot. And again, so this is where we're getting possibly 3 observations in a night, but definitely pushing to high air mass and then observing much later in the night. And again, you can see this can really hurt supernovae because we're getting much less area per night to discover supernovae in. And they're labeled with nights off. So nights off 0 means we're trying to get long gaps every night. Long gap 7 means once a week we're trying to get long gaps. And we've got on the right, it's doing it for all 10 years. And this group on the left is starting in year 5. So lots of ways we can, so if we do it once a week after 5 years, it's a very minimal impact. If we do it every day, we destroy supernovae. So we can balance. And once again, we need a metric that balances out. There should be something that trends upwards both ways here. So we need a science case for sampling at 4 to 7 hours to kind of justify this strategy.
Can you remind us why the 4 to 7 hour gap experiments were done? There was something in the back of people's minds when they said, let's try this out.
It's a time scale that we don't sample. There's almost 0 sampling at that time scale.
Discovery potential, basically.
Yep. Yeah.
Yep. Gotcha. Okay.
Cool. Yeah. Thanks. Yeah. Okay. And then again, the Presto color. So this is again getting triples in a night. And you can see we're testing, trying to get a third observation at 1.5 up to 4 hours. At half-hour time steps. So, and then if it's plain, we're doing our regular filter pairs. Mix means we're doing farther spaced filters. So G plus I, R plus Z. So we've got a larger baseline on that color. So those are the mix. And then there's ones that are labeled half, which I think means every other night. And so again, you can see if we dedicate a ton of time all the time, we cut our supernovae in half. If we do it half the time and do only large hours, it's still a hit on the supernovae, but maybe not as bad. And we can turn this down to, again, be like the long gaps where we would do it once a week or something like that. And yet again, we need a metric that says why these are positive. We need a generic transient classification metric, or just pick your favorite transient object and write a classification metric for it, so that we can say, oh, we will successfully classify many more of these types of objects in these simulations than in the baseline, because there should be such objects out there. Okay. Oh, and the longer gaps are better because we can't do multiple 4-hour gaps per night. When we do 1.5-hour gaps, that it just keeps going for much of the night and boxes out lots of other observations. Okay, so conclusions: we see clear trends, and we have plenty of gaps in our metric coverage where we would like new metrics so that we know and can quantify those trade-offs. We know there should be some good science going on, but we don't know what all of it is. Okay, thanks. Any questions?
Thank you, Peter.
Let me ask, I mean, you chose those three metrics to show, and as you said, there are many more metrics to take a look at. I don't know, well, I imagine one can make equivalent plots, and I wonder if there's sort of qualitative things to learn from them that are not captured in the 3 metrics that you've shown. Of the metrics that we already have, I'm not speaking about the metrics that need to be written that you were making reference to.
A lot of them correlate. So
Yeah.
it's basically the supernovae are a good tracer of pretty much all the wide, fast, deep science, right? It's because they're related to depth. So pretty much all the cosmology correlates with the supernovae, even though.
Is that right? Because supernovae, it's a single visit depth, but the 10-year depth, does it correlate with 10-year depth and uniformity, and things that large scale structure and weak lensing really care about?
Right. I mean, it's basically, if you get more visits, you get more supernovae and you get more depths. So,
Yeah.
so it's weakly correlated. It's a big boost for supernova. It isn't always a big boost for like the weak lensing, but it tends to be a boost.
Okay. So supernovae are more sensitive, as it were. I think it's
Yeah.
yeah. Okay.
Yeah, and yeah, there aren't a lot of other science metrics that show big trends right now. Basically, it's I haven't looked in depth at all of them yet, but these are kind of the ones that can show big changes. Otherwise, we get splitting hairs of how much is a milli-arc second per year in parallax worth. And I guess the other big thing is the solar system metrics, which we haven't finished running yet. Those will show some large trends. Okay.
Thank you, Peter. I linked slides for science collaborations report. I don't know who will start. It looks like the first one to be discussed is desk, but there are a few slides at the beginning that sounds like maybe Fed or someone else to open it.
Not me.
Not you. Who is going to share that? Who is the first speaker? Should I share the slides?
Yeah, that would work. Currently it's AGM, but there aren't any slides. So I don't know if actually somebody's presenting another slide deck. And then after that is desk. But I'm happy for you to share the slides.
Okay. Can you see them?
Yes, you can see slides.
So who are we? That's Federica.
So I think I know what happened. I think this is a slide deck that had been reused from a slide deck that I had made in the past. But I don't think anybody needs to hear who we are. We are the science collaborations, and this slide deck was composed on the basis of the science collaborations, discussions, and needs. And so without further ado, let me give way to the science collaboration slides.
All right. Well, I didn't know that there are as many as 2,000 members. I thought it was closer to 1,400. This is news.
No, there are, and a lot of them are in desk. Desk itself contributes for about a half of that number, but other science collaborations have as many. Actually, TVS currently has over 300, and all the science collaborations, most importantly, are growing and growing quite rapidly.
Excellent.
So join us if you're not a member.
Okay, then let's move on. SDF. Okay, informatics and statistics declined to provide input at this date. Well, originally we didn't put them on the list, so maybe they got mad at us. Us as in royal us. It was my fault. AGN. Okay, so I'm confused now.
So Zeljko, there's a question and answer slide at the end of each of the pairs of science collaborations. So this is the end of the AGN plus ISSC section.
I see, but there are no slides.
No, there was no content added.
Oh, I see. So we can go straight to desk.
Yeah, that's right. Yeah, these are copied out of the plenary slides from the August meeting.
I see. Now I understand. Okay, there are 3 slides from desk. Who is speaking to them? Humna.
Yes, Hamna. I'm Hamna Awan. I'm speaking on behalf of desk and specifically the Observing Strategy Working Group. So before sort of giving an overview of our impressions of the CSC report, I just wanted to highlight a little bit of the science that sort of is happening or is being planned and happening in desk. So desk science relies on various cosmology probes, and they include static probes and transient probes. The primary static probes include weak lensing, large-scale structure, and clusters, whereas primary transient probes include type 1a supernovae and strong lensing. But we also have other transient probes like kilonovae and gravitational wave sources. Just to plug here, the ASTER 2020 recommendations actually made Rubin transients a major focus. So I think transients in general and transients for cosmology are just very interesting in general. Given sort of the scope, both WFT and DDS are critical for both kinds of probes. And there's quite a bit of work going on in the Observing Strategy Working Group, and I've linked a few of the publications, as well as collaborations and connections across the science collaborations. Next slide, please. So just like a bullet list of all the things that we're really happy about in the SCOC report, or the recommendations. So the first one is the decoupling of the low extinction WFT regions versus high extinction. This is something that we've been really pushing for because desk science really needs low extinction regions because we are focused on extragalactic sources and extragalactic science. So this is really encouraging to see that, you know, sort of even the baseline actually is using the extinction limits as the limits to define the WFT. The second thing is testing, pushing the limits on declination bands. So as you know, like there are basically different simulations may go up and down on the declination bands, and that could be really helpful for us because we really would like overlap with DESI, which is a spectroscopic survey at higher declinations. And so that's something that we're really excited about as a possibility. The third one is recognizing the critical role that DDS will play in WFT science. Of course, DDS are really interesting, like in their own right for, you know, transients, but for instance, photo-Zs in WFT need to be calibrated and DDS will play a critical role for that. So seeing that sort of recognition and therefore the emphasis on DDF optimization is really great. Now, fourth point, field revisit in different filters on the same night. This is really good for transient classification and supernovae classification and distances specifically. So having a color measurement for all observations is great. And then finally, it was mentioned that it'll be good to revisit dithering in commissioning, and that's phenomenal because specifically rotational dithering is difficult to kind of pin down without commissioning data. So we are excited about the possibility and the emphasis on testing dithering during and after commissioning, right by the end of the commissioning. Next slide, please. So the aspects that that DESC is sort of concerned about and is working on, the first one is rolling cadence. So as sort of has been elaborated on a little bit, rolling cadence is very promising in terms of alleviating a few of the tensions, specifically, for instance, depth versus area trade-off, alongside improving cadence, right? We saw that number of supernovae detected increases with the rolling, which is great. But how rolling is implemented is really important, both for static and transient science, right? And the one question that specifically do we think that is missing from simulations is the 1.5-year buffer that's chosen for astrometry at the beginning and the end of the sort of the rolling simulations. And it would be great to kind of play with that as well.
Okay, perfect.
Wonderful.
Yeah, probably see me over here. Yeah.
Okay, sorry. Basically playing with that 1.5-year number as well. Related to cadence, rolling cadence is data releases. So as I mentioned, rolling cadence has a direct impact on static science specifically because static science depends on uniform data releases. So for instance, if we want to do our cosmology analysis at Y1, Y3, Y6, Y10, and those are sort of just arbitrary numbers, ideally we would want uniform data releases at those intervals, right? But if those intervals don't line up with the rolling period, then basically we will have non-uniform data releases to work with. So then the question is, who will produce the uniform uniform data releases versus the comprehensive releases, which will basically contain all the data? What exactly needs to happen in terms of infrastructure? Who will do what? So that's like a concern that is tied with rolling cadence that we have. And the second point that we want to think more about is the DDF optimization. As I mentioned, DDFs are critical for both static science and transient science. For transient science specifically, the desk science suffers with DDF allocation with less than or equal to 5% of the time. And that's assuming that we have the desk optimized cadence, filters, exposure time, etc. So the cadence needs to be optimized alongside hopefully pushing for more allocation. So here I want to give a short plug of the DDF community session, DDF optimization community session tomorrow at 10:45 a.m. Pacific time. If you're interested in DDFs in general as well, please join the channel. That's hashtag DDFs to kind of stay in the loop. So these are the two main topics. I do want to mention there are internal tensions in desk for static science versus transient science. And of course, we have to figure out sort of the trade-off. And I think that exercise is going to be something that we share with, outside desk as well. So we are looking forward to collaborations and connections on various aspects as we figure out the trade-offs between the various factors. And next slide, I'm happy to take any questions or concerns. Thank you.
Thank you. I'm trying to advance on the next slide. There we go.
Yes, Meg.
Yeah, I had a quick question about you said data releases. You went, we want to have a release on X year, X year, X year. Is that a desk release? Because I'm wondering, is that you're talking about your internal data product releases? Because if you're off year, you could wait, right? And then wait till the half year you're missing is processed in a next data release, correct? Did I misinterpret that? I'm just trying to ask, wearing my SCOC hat, what do you mean by data releases? Because in terms of desk.
So the thing is that, like, nominally say we have yearly data releases, right? From the data management. So year 1, 2, 3, 4, right? It's possible, for instance, that in Y4 release, that basically we don't have uniform data. So either we would have to throw out the data or wait an additional year. And that is something that may not be optimal, right, for science itself. And like, how exactly do we go about? Will we always have to like throw out some of the data, in the intermediate years? Like, how exactly would that work and what impact that would have on our science itself? Because a lot of the products are also coming out of the data management that we will have to reprocess without the additional data that makes the data non-uniform. So there are just like a few details, at least, that need to be sort of ironed out in terms of what would work in order to get science analyses out sort of in sync with the data releases.
Thanks.
Are there more questions for Humna? I'm sharing screen, so I cannot see my Slack. If not, thank you, Humna, for this excellent summary. Let's move on. Next is solar system.
Hi, Mike Kelly here. I'll be presenting the Solar System Science Collaborations summary. So first is we're really happy with the updated footprint, including the North Ecliptic Spur is one of our priorities. So that it's being carried forward is excellent. We do want to look at the variations in the number of visits. So that was something Lynne summarized, how the NES had to have an increased area, but the number of visits decreased to compensate. So we'll be inspecting that and how that affects our metrics. Of course, the North Ecliptic Spur is really important for outer solar system science, active asteroid population studies, Planet 9 search, probably a couple of other things. So next slide, please. With respect to what kind of time it could be recovered in the future, possibly the low solar elongation twilight survey. So we really are excited about this. It has some of us are, it enables some niche science cases. So just a reminder, this plot here shows the solar elongation histogram, and things that have orbits that are interior to the Earth or even just near the Earth do not get that far away generally in solar elongation space. So having a survey that's getting 60 degrees or even closer to the sun would be excellent. So any time that can be dedicated to this will definitely be useful. With respect to how the first year operations may not execute any of these surveys, that's totally acceptable. wide, fast, deep operations should be a higher priority. But certainly there's room, hopefully there's room for testing these things and commissioning. So next. With respect to U-band observations, exposure times up to 1/50 seconds are advantageous for gas. So we do have some science cases that could use that. So if, as long as it's doesn't impact our other metrics, that sounds excellent for us. Beyond that, it does seem to impact discoverability of objects, and those are our top metrics. So filter pairs, just solar system objects are generally brightest in the redder filters. So adding G-band observations can be beneficial for some things. Again, there's gas emission bands that could benefit from those observations, but we do want to, we have to temper that with that it could be impacting Kuiper Belt object discovery, which tend to be very red objects, and some light curve inversion metrics. Next. Nightly pair separation going to 33 minutes is a good balance for all a solar system. We can detect some proper motion out to 100 AU or so. So that looks really good. Next. Long gap scenarios. Yeah, so we're a little bit concerned about this. Even if it's something that doesn't affect the first few years. And that's because, well, first of all, the longer time between pairs means we have fewer nightly pairs that are well optimized for solar system science. And that means a decrease in the number of comets, near Earth objects, potentially hazardous asteroids, interstellar object, or it could mean that we'll have decrease in these populations, because these are the populations that are discovered throughout the 10-year period. Main belt asteroids, which dominate the numbers in the solar system, are mostly discovered the first few years. So that's something that we want to avoid, and we'll be looking at that in the future simulations. Next, please. For rolling cadence, the more extreme versions do kind of impact our metrics, but we'll be looking at the rolling cadence in general. It's probably that the less extreme versions will be fine, but we'll be looking at that. So that's it.
Thank you, Mike. Questions for Mike? I see.
Yeah, can you?
Anut?
Yeah. Thanks for that. I was wondering, so if you don't detect solar system objects, particularly in the first couple of years, I guess that's bad for solar system science. It's also bad for transient science, right? Because those are then contaminants for identifying those. I wonder if is there a metric that considers sort of contamination from the transient perspective? This is a question for everybody, I guess.
Yeah, I don't think I could answer that. That's an interesting point.
That is a good question. I'll have to think about it.
We don't have a metric that does that, but it is true that the main belt objects are the majority of the contaminants. And I think the things that are discovered later are really interesting, but they're not the majority of the objects. So it's true, you will still have contaminants and you will still have those there, but it's a little bit different.
I think the brokers, the people that are building the brokers would have this answer, right? And I'm thinking of Ridgway all 2014 basically was looking at this. What is the contamination to transients from alerts, from repetitive stochastic events and asteroids? So I think the answer is out there, even though it's not perhaps a metric.
As far as I know, at least Antares and I'm thinking other brokers rely on solar system objects being detected. and identified. Otherwise, the contamination swamps their rates.
I see. And you should know because you are on that paper, right? That I just
yeah.
Okay, we'll move on. Next is strong lensing.
Hi, everyone. So it'll be both of us that talk. I will just talk a little bit about our official Cadence note and what do we think about the SCOC recommendations. So I'm Timon Gita, and Graham Smith, who's also here, will tell us about lensed neutron star, kilonova, and TOOs. Okay, and we will finish with some additional concerns. So next slide, please, Zeljko. So we submitted an official strong lens in science collaboration Cadence note that dealt with our static science. So basically finding lenses. So strong lenses are rare, but they're everywhere. So naturally, one of the main things that we need in the survey is wide area. But second, and not least important, is that we need very good image quality, and we cannot stress this enough. I mean, so factors around a seeing of 1 arc second, if we do improvements in 0.2 arc seconds in the median seeing, we get like twice the number of lenses. Okay, so it's very important. And here we say that particularly in the blue band. So here our concern is that when improving seeing, for example, for the redder bands that are of importance for many other science cases, this is not done at the expense of the G band. Why the G band? Because usually our sources are star-forming galaxies or quasars that tend to be bright in the G band. And then we also need blue sensitivity because of the same reason. So here you can see a plot of some of the different families that we explored for the Cadence note of different median seeing and then median-based epoch seeing, saying, say for the first year, if you wanted to find all our lenses, okay? And we suggested that some of these families were slightly better to find lenses, since as you can see, the median seeing, particularly in the G band, is not sub-arc second, but it's straddling the 1 arc second mark. So next slide, please. So regarding these 3 points, these 3 main points in finding lenses, we saw the recommendations. And regarding the wide area, I think it's a good thing. They will optimize the low extinction area rather than just an increase. That should work in principle for us. The SCOC recommendation has no discussion whatsoever on image quality, which is, as I told you, one of our main concerns. However, there is some blue skewed simulations, which we also appreciate, that we are going to, we still need to test, okay? We don't know if blue skewed means that we have more images that we can pick better seeing images for the G, or how is the seeing in general optimized. And that's it from my side. And now Graham will tell you a little bit about the TOOs.
Thanks, Timo. Hi, everyone. So my key message is quite simple, that discovery of gravitationally lensed gravitational waves is a great motivation for deep target of opportunity observations with Rubin. The basic concept is familiar in terms of how of localizing. We have the example of a binary neutron star being localized to a host galaxy a few years ago, and the role of deep Rubin TOOs in the context of lensed binary neutron stars would be giving us the ability to localize a candidate lensed binary neutron star to a lens. And so some of the key points here are that our latest predictions that have been updated just in the last week following the GWTC 3 are that LIGO should be capable of detecting one of these objects per year in the mid-2020s. And this is obviously well matched to early the early years of the Rubin survey. And as I'll show you an example light curve in a moment, the lens kilonova counterparts tend to be very faint. And so we need potentially up to 1 hour per pointing, which clearly implies very careful selection of these candidates that I'll just say a couple of things on in a moment. Overall, as well as hopefully attracting your attention that this is a great motivation for deep TOOs, we therefore also recommend and would like to get involved in including these objects and deep TOOs when testing the impact of TOO microsurveys. Next slide, please. Here are a few figures just to sort of give a slightly more quantitative and visual impression than these bullet points just a moment ago. So you can see the cumulative in the left plot, you see the cumulative number of gravitationally lensed binary neutron star mergers with time. And you can see that one is here. And so the first detection should be coming in the mid 2020s. If not actually in 05, then following on from that. Selection of candidates needs to be very careful because the kilonova counterparts will be very faint and require quite a bit of time per pixel, as it were. So selection of the candidates as being in the mass gap here, actually, so you can't see my pointer, can you? The lens binary neutron stars are basically magnified into the mass gap between neutron stars and black holes. So we already get in practice in selecting these objects in 03, and we'll be doing the same in 04. And I've picked out here on the right in the light curve plot, the main curve to look at is the heavy black one, which is picking out objects that LIGO put up basically at 1 gigaparsec away when ignoring lens magnification in low latency. This is for a 2017 GFO-like kilonova, and therefore this is actually optimistic. And so more typical kilonova based on various models would be fainter than this and therefore peaking somewhat below the Rubin single visit depth. Next slide, please. I won't say a huge amount to this slide, except just to draw attention to a bunch of different issues that have already, some of which I've already mentioned in passing, around careful vetting of candidates, but also if we do early, if we have deep TOOs early on, then this raises questions about reference imaging. Need to be careful about the false positives and various other issues around the data analysis as well that we're getting ready to work on and would love to collaborate with people on. So the important message as well is if people have similar interests around deep TOOs and some of these issues, it would be great to chat and work together. Okay, back to Timo.
So next slide, Zeljko, please. So there's, yeah, we have a few additional concerns that we will touch upon in also tomorrow in another in some of the other sessions. The first one of them, and I'm already seeing messages in the Slack, but how is this image quality measured and optimized? Okay, this is something that we don't quite understand, and that concerns us a lot. For example, there's there are new simulations with variable exposure time. Okay, when they reach the required depth, they will stop making observations. Is that seeing optimized as well, or only depth of the optimized? So that's something that I would be interested to discuss. Also, something that we suggested in our Cadence note was that we could follow some optimized image quality survey strategy for the first year. That would be way more than enough for us since we need to find the lenses. There will be, I will have some discussion about this on a session tomorrow on the trilateral AGN TDS and strong lensing session tomorrow. We're a bit concerned about this new 2-band rolling baseline, since I've seen in general that quasar time delay measurements and quasar microlensing are affected by rolling cadence, but it varies a little bit on the different strengths of rolling. So I need to test this already still. And finally, we recommend to include deep target of opportunity observations when simulated impact of the TOO microsurvey on the survey cadence and observing strategy. Thanks. I don't know if we have any questions. I think we had a few.
Questions for Timo?
Well, this first bullet that he has here on the image quality, you were concerned that there were now simulations that were exploring image quality variation, and I guess my question is, what would you imagine such a survey to do? Do you want to say when the seeing is good, we preferentially go to the shorter wavelength bands, for example? Is that what you might have in mind?
That would be ideal for us, yeah.
Yes. Okay. At the moment, can one simulate? Does one have in the simulations an a priori model of what the seeing might be on any given night and use that to make decisions? Is that something that exists within the simulator?
Well, so in V1.5, I think it was, we had a good seeing set of simulations where it wasn't so much that you predict when it's going to be good seeing and then plan to make observations, but when it is good seeing, because we do know that when we're observing, if you haven't had a good seeing visit in that part of the sky, then we said, okay, this is an extra priority for this field. And then it still gets weighted in with other things like, do we need to take a visit to that part of the sky and so on. But yeah, so we can add a relatively simple kind of thing like that, where we're saying, if you haven't had good seeing visits, then add some. I think it's a little bit harder to say, oh, if it's good seeing, always take a visit in this bandpass, because then you end up not having good seeing visits in other bandpasses, and it's harder to balance the time. But doing the question like, oh, if we haven't had good seeing, do take a visit, that's a little easier.
So that would be actually very good for us. So our concern is to get a very high quality template image, to find our lenses. The deeper it is, the better, but we do need all the area with good seeing in preferentially all bands, or at least GRI. So that strategy would be fantastic.
Yeah, we already give preference to R and I bands because of weak lensing.
Exactly. So that's what I'm afraid of. That's why we're stressing so much the G.
Right. So I think it would be straightforward to change baseline to include G band 2, and then we compare the baseline we have with that experiment and see how much better or worse it does for other science programs. Lynne and Peter, do you agree it would be straightforward to add such a simulation to the list of future simulations?
Yeah, we've done it in the past, so we had to 2 or 3 lines to drop in and try it.
I would note, I don't think we are prioritizing R&I band for good seeing in the current baseline. The seeing is not really one of the things we consider as a primary basis function. So this would be a different sort of simulation. I mean, but yeah, we've done it before. We can definitely do it again.
And if I recall, the impact was very minimal. Like it didn't adversely impact anything, and we didn't have anyone at the time clamoring for it. So now we have people clamoring for it. So it should be a fairly easy swap in.
Any more questions for Timo and Greg?
Well, I would imagine that that metrics that sort of look at results at the end of 10 years may not need this kind of fine tuning, but metrics that look after a year or two at specific data releases may feel this is a little bit more important.
I think you're right there, Michael, that it was not a huge difference after 10 years, but there was more of a difference in any particular year. So it's worth thinking about for sure.
I don't see any other questions.
Thank you very much. This was good.
Thank you, Timo. Moving on. Galaxies.
Yeah, so Harry Ferguson here. So you'll hear a little echo on the next slide, but basically we're quite happy with the direction things are headed. Longer U-band exposures were always a higher priority for us, so that looks great. Greater overlap with Euclid is a high priority, so changing the footprint to improve that is a good thing. It's nice to see the Virgo cluster microsurvey is going to be included in future investigations at the YPAS deep depth, so we're all happy with those. Next slide. The first one is this sort of, echo, although a little bit different. So this was in our white paper to the SCOC to think about optimized seeing in the first year. So basically, one way to think about this is an insurance policy for a good start on the static sky catalogs, because peak finding is the first step, and peak finding is very sensitive to the PSF. So a very, I think, achievable goal is just to put a floor in that makes sure that you get at least a quarter of your R-band exposures taken in the best quartile of seeing. And then you've got a floor that if nothing else is there, you've got a uniform starting point for your catalogs. Within the discussions in the collaboration, we were divided on priorities. If you add another band to that, which band it might be, whether you would go and say G and R, or whether once you've gone to adding G, you might be better off doing G and I, so you have a bigger baseline between the two, and nobody could point strongly to one or the other. So I think we would say maybe optimizing in G is your next priority after getting one of the red bands as your first priority. And whether that's R or I, I'm not sure we have a strong feeling. A lot of our science is high redshift, so that pushes us to the redder band as being the higher priority. On the other hand, signal to noise tends to be a little better in the R band. So I would say that particular goal there is, as say, an insurance policy. It's not particularly ambitious, might not happen automatically in the first year unless you pay some attention to it. You could try to be more ambitious, but obviously you're trying to balance other things. Second one is also thinking about the first year. So U-band calibration is particularly tricky. And so it'd be good to get a good baseline there of some minimum of exposures taken at low air mass in photometric conditions on every spot in the sky. And so basically take advantage of good conditions to be sure. It might be, as long as you have enough reference stars, it might be that one exposure is sufficient, but we've not looked into that in detail. I would say it's probably hard, and we certainly haven't done it, to come up with high-level science metrics that would drive either of these. It's simple to think about how you might add weights to the scheduling system, or maybe evaluate it post facto just on the simple question of, are you achieving this or not? But to connect it to the higher level science, I think we haven't tried to tackle and haven't really figured out how we might do that. We do have some things to say about DDFs, but we'll save that for the session on the DDFs.
Thank you, Harry. Questions? Okay, then let's move on. Next is stars Milky Way local volume.
Okay, thank you, Zeljko. I'm representing the feedback thus far on the SCOC report from stars Milky Way local volume. Most groups within our collaboration that have developed metrics inside or outside of MAF are still working on rerunning their metrics on baseline version 2, with one exception I'll present in a few minutes. So I'll provide some immediate feedback on that we have received. To first order, the new baseline is a big improvement for most, but not all, science in the collaboration, or it does not seriously compromise areas of our science that do not require particular footprints. In particular, improved coverage of the regions in the galaxy where most of the stars are, so the bulge, plane, and Magellanic clouds, has for a long time been a big request from this community, and it's been really good to see that this has been implemented to some extent in the new version of the baseline. So for much of our science, the new default footprint is a major improvement. And as you can see just from the science topics that we have working groups for, several of those important topics are sort of in general improved with the new footprint. Next slide, please. So Peter showed some of this already, I think, but just to use proper motion uncertainty as a proxy for the kind of improved sampling and improved depth, I'm showing the version 1.7 baseline and the version 2 baseline proper motion uncertainty at 20.5 magnitudes against the one of the figures from a nice Cadence note by Rachel Street, who polled the 2018 Cadence notes to come up with these areas in the sky at which there has been particular interest. And you can see that just by comparing 1.7 to 2, certain areas of high interest, like the Magellanic clouds and at least the southern bulge, are now covered quite a lot better than they were in previous versions. So that's very encouraging to see. And my prediction is that the metrics, when run on version 2, will show that for SMWV science that focuses on those areas, this will improve the science return that we get. Next slide, please. In addition, there are some science metrics, including the one that has been mentioned already that is in math, the cool brown dwarf detection via parallax. This science case is an example of a science case that does not depend on footprint very much, does not appear to be seriously compromised, although I guess I'll let the brown dwarf experts decide what we mean by seriously compromised. But just to do the comparison, version 2 has about 7% fewer cool brown dwarfs with wideband uncertainty less than the threshold with good parallaxes. So this may be livable, and again that's up to I think the solar neighborhoods experts to debate. Next slide, please. So I mentioned there was one group in SMWV that has rerun its metrics on the new baseline, and that's the group of Loredana Prizanzano, Sara Bonito, and others who have run their metric looking into young stellar object discovery. And just by comparing the baselines between the three baselines, 1.5, 1.7, and then baseline 2. Baseline 2, the new one, offers a substantial improvement over 1.7, although perhaps not quite as good as the 1.5. So again, the question of whether that sort of 10% loss compared to 1.5 is acceptable is one that I think we have to work out. Next slide, please. Okay, so this is really my last collection of points. There have been a couple of developments during 2021 that may be of interest to people on this in this meeting. One of which is that for SMWV science, we're often interested in three-dimensional extinction. Questions like how far, to what distance can you observe to some signal to noise, including red extinction as a function of distance. And so you'll notice in the Cadence, several of the Cadence notes for this collaboration, that they use a three-dimensional extinction map, which has been packaged to interface with Rubin Sim. And so the 3D extinction map that was used in those Cadence notes, plus query tools to use it for Rubin Sim, are being prepared at the moment for incorporation. That's currently being led by Alessandro Mazzi at INAF Padova. The second development that may be of interest to people, and I think Lynn mentioned this a little bit earlier on, is that the Rubin Sim predicted spatial confusion limit probably is about right if you have the right crowding error parameter for that metric. Comparison with DETCAM images that are confusion limited in the inner bulge suggests that using the crowding M5 metric with crowding error 0.25 magnitudes or so reproduces about the 50% completeness limit in a single filter. So for example, for the R band completeness limit, you would use crowding error 0.25 magnitudes to reproduce roughly what we achieve with DETCAM. There is a metric under development to predict the confusion limit for colors because the luminosity functions correlate for different colors that our crowding expert Knut Olsen has been developing, and that's I think in the pipeline to come out. So there've been a couple of developments during this year that have been very relevant for at least for galactic science metrics against which baselines like version 2 can be tested. But I'll finish with a few of the open issues that we know about in the collaboration, which are intended to be addressed by metrics. Very importantly, by metrics which will be incorporated into Rubin Sim. And there'll be a session tomorrow to discuss this in a bit more detail. There's at least half a dozen galactic metrics that have been either under development or that have been actually coded and have been used in Cadence notes that have not yet made their way into math. And so one important thing that we know we have to do is to convert those metrics into Rubin Sim now, into Rubin Sim, so that they can be run on all of the runs. But just a few of the questions in terms of the science we want to do that I think still need to be addressed are listed in the sort of beige rectangle in the slide here. Filter balance in the plane bulge and magnetic clouds. I think we've had that discussed already at this meeting, but examples include some of the static science cases require as high accuracy as possible in all the filters for color work, for example. And there might be a trade-off there against variability if other science cases require very intensive monitoring in one or two filters to get variability. One question we've heard a little bit about today, which is also, I think, very much on our minds as a collaboration, is what about the plane outside the bulge? We probably don't want to go below about the current baseline, which I think is 0.27 times wide, fast, deep, because that's sufficient to do variability science, accurate proper motions throughout most of the plane. Some cases prefer even greater coverage, maybe half times wide, fast, deep or more. And I think these issues of how much you can live with for that science, I think are going to be important. Like I said, there are known metrics that are in preparation. I think Lynne mentioned the young stellar objects metric in a Slack chat that is in the process, I understand, of being converted to Rubin Sim. But there are areas for which we know that we still need metrics for the science area. One obvious example is the interstellar medium itself, which I think by definition requires a certain level of precision towards high extinction regions. And so that's an area that we know about that needs some development. Among the feedback that we've received, there's some excitement about rolling Cadence, but I think others have said in this meeting, how that's implemented in most appropriate ways is something that needs to be explored. Switching gears a little bit, for galactic science, short exposures may be quite important, both to measure bright objects, or even bright foreground objects in their own right, but also to predict and to calibrate the effect that those have on the rest of the field. So if you have some very bright stars in the foreground, those can impact the photometry and astrometry for objects quite some way away from these objects. So it may be that short exposures are required for calibration, and it might be that they're required for calibration early in the survey. I suppose one of the unknowns for this is whether this can be adequately handled during commissioning. But I think for the moment, whether we have to do short exposures early is something I think it would be good to know for galactic science, or for any fields in which there will be a bright foreground of objects that should be observed. And a related issue then is when those short exposures would happen. And this also brings us back to this issue of trade-off for high MS observations for parallax, and what do you do with the twilight time? This may be an area to be explored. And finally, another point that I think would be good to incorporate in the current or maybe future generation of metrics is that the distribution of seeing that one actually obtains in a region is likely to matter. I think at the moment, for example, the confusion metrics that we currently use take the best one or two images, best seeing one or two images towards a particular location. But there's the question of, I think Harry brought this up quite well in his galaxies presentation. It's likely to be better to use the best 25% of seeing observations for crowded regions. And then I guess the question becomes, how do you allocate that? Where is the threshold? So I think returning to the seeing distribution is something we're interested in doing in SMWV as well. Okay, so that's I think the feedback I had. Generally, for most of our science, we're quite happy. But again, it's really up to the metrics to show this. And with that in mind, as a very brief plug, there will be a short half-hour session in the community feedback section tomorrow on missing metrics for brackets galactic science. I've put brackets around galactic because I think it's true that still a lot of the gaps in the metrics are in galactic science, but there's so much overlap that anybody is welcome certainly to participate in this session. I think it'll be helpful to see who's working on what and kind of what the steps now are going to be to produce the metrics by this end of 2021 target that Zeljko and Lynne have pointed out. Okay, thank you very much for your attention. I can take questions now or after TVS has spoken.
Thank you, Will. Other questions? Meg? See a hand from Meg.
Yeah, just wearing my SCOC hat on. So if I understood you right, you were saying the only reason you want these very short exposures is that you're concerned about that calibration is going to be bad. And that photometric calibration is a potential issue. Because I would think it's an issue for everybody that, like, if magnitudes cannot be measured correctly when there's a bright star in the field, that would mean that we've not hit the SRD requirements, right? The software is not producing things that will hit the SRD requirement. Am I misunderstanding something there?
No, thanks for the question. There are scientific reasons as well. Like there are fields for which, for example, bright giants might be genuinely of scientific interest. We want to measure those well, even if they saturate at the program exposures. So there are scientific drivers for short exposures, but indeed for the galactic fields, I think the chances are higher that there will be a bright foreground population. Looking along the sort of not too far from the galactic midplane, you will probably get more foreground stars than looking at very high latitudes. So it's an issue that I think we're particularly concerned about, just because so many of our fields will suffer from this. Does that answer your question? Or?
Yeah, so it sounds like if commissioning showed that was not an issue, there would be less, one of the main drivers would be removed. There would be other science cases, but a very strong case for this would be potentially removed. So that we should make sure that this gets tested heavily in commissioning to help answer that question.
The way I would frame it would be, I think it's essential that this get tested in commissioning to deliver on the photometry that we require. But there are also scientific cases that would benefit from monitoring short exposures as well.
Yep.
And I see Fed's pointed out in the Zoom chat that there was a 2018 white paper on planet transients that also suggests saturation. and speculated the 15-second snaps. That's true. There's also at least 2 cadence notes that mention this. Claudia Reiteri, I believe, is the first author on a cadence note that mentions saturation, and then we have one on short exposures, Clarkson et al. From 2021 as well.
There was certainly quite a lot of discussion of the need to do short exposures over the entire sky to tie to the photometric system of bright stars. Whether that's needed for calibration in the absolute sense, I don't know what the current thinking is. Zeljko may have an opinion there.
Right now, we believe that Gaia will help greatly. When we designed the original program, we could not count on Gaia, but now with Gaia, people are showing you can transfer, you can synthesize UGRIZ photometry-based synthetic Gaia magnitudes within few milliamps.
There's still the issue of, sorry, I didn't mean to interrupt, please.
We will definitely check that in commissioning. So
okay.
If there is need for short exposure time survey, we'll do it.
Okay. That's encouraging to hear. If there is a need for a short exposure time survey, I would recommend it happen early, because it would then impact the calibration, I think, of your artifacts near the bright object. So it may be something good to solve as early as possible, even if it's not done during commissioning.
If it's purely scientifically driven, then I think it could be considered as one of those nano surveys that we discussed earlier. Someone used word nano for those that are of the order 0.1%, like mini, micro, and nano surveys. So you could propose for a few nights and do whole sky.
I think I agree. If it's purely scientific, possibly there may be a question about urgency, maybe. But I still think the technical urgency would be a strong driver for doing it early.
Are there more questions for Will? Okay, if not, thank you, Will. We'll move on.
Thank you all.
Next is transients and variable stars.
Hello, everybody, and thanks for this opportunity to speak. I'd like to summarize the work that's being led within TVS by our Survey Strategy Task Force, whose members you can see credited on the screen. Next slide, please. I do want to point out that many TVS members have contributed to all of the survey strategy work that we've been doing, from white papers to cadence notes to metrics. So I wanted to acknowledge their contributions and the productive collaborations we have with the other science collaborations. And in reviewing the phase 1 recommendations, we realized that the SCOC has incorporated a number of our proposals and recommendations at earlier stages. So I wanted to convey TVS's appreciation to the committee and the MAF team for all their help and advice. Next slide, please. So the presentation will have 2 parts. In the first part, I'd like to summarize our specific responses to the phase 1 recommendations as described in Zeljko's recent document. And then I'd like to go on to describe some of the work that TVS and our collaborators are still working on in response to the SCOC's feedback. So to start with the phase 1 recommendations, we noted that this document is divided into the 7 questions, so we've arranged our responses the same way. But while I present the summary today, if you're interested in going into any of these questions in more detail, you can find a lot of it reflected in this document that was led by Will Clarkson, which was a collaborative effort to synthesize the recommendations from STARS and Milky Way and TVS following the submission of the cadence notes. Next slide, please. So regarding the question of survey footprint, thank you to the SCOC for considering the mini survey of the galactic plane and Magellanic Clouds. We strongly support the inclusion of that in Baseline 2.0, and that will enable a wide range of science of interest to TVS members. We support the optimization of the survey region by considering extinction rather than set boundaries, and the recommendation that the cadence for each of the different surveys should be optimized separately for the low versus high extinction regions. We noticed that that is scheduled for the next phase of the SCOC's work. We also appreciate that the baseline 2.0 provides more observations of a wide area of the galactic bulge and the Magellanic Cloud, and that's certainly of value. But we did want to point out that there's still quite a range of the galactic plane, which is of very high interest, but which still receives fairly low cadence. And I want to point out that this is important for comparing populations in those central bulge region versus other regions of the galaxy, which have different star forming histories, etc. And so we have actually revised the footprint that we were recommending for the combined survey region to include some pencil beam fields, which are shown on the left in the plot there. And the motivation behind doing this was to provide that wide comparative area of different regions within the galaxy, but at the same time minimize the amount of area covered, so not to take too much time out of the survey. So that's something that we are continuing to explore. Next slide, please. Of course, we recognize the inherent tension between the time dedicated to different survey regions. So there is so much to go around. And we know that the SCOC has to strike a balance between the different components. We did want to emphasize that there are strong potential synergies between Rubin and other major survey facilities, excuse me, particularly the Roman and the Euclid missions. So we encourage the SCOC to coordinate with those missions at an earlier stage because that is likely to take time to actually get that working. We note one proposal in particular for higher cadence survey observations of star forming regions was designated at a micro survey, and we understand that those will be incorporated in the survey strategy at a later stage. But we have some concerns in this particular case because of the complexity that it represents for observation scheduling. And we think it's therefore valuable to explore this as early as possible rather than postponing it to later. And since that's a specific science case, we'd like to propose that TVS's SCOC liaisons meet with the authors of that particular study after the workshop to discuss it. Next slide, please. In general, the main concern for TVS members regarding U-band exposures is that LSST should cover a wide dynamic range as similar to what Will just discussed in his presentation. And avoid saturating bright stars, which are of great interest to us. But it was noted that for some cameras, some of the photometry can be recovered for saturated objects. So that is one way that this concern might potentially be mitigated. Next slide, please. We noted that the SCOC plan to optimize the amount of time dedicated to each filter in the next phase of their deliberations, which is of course fine. And we strongly recommend optimizing this differently for the different regions of the sky, broadly, but not exclusively based on extinction. However, while we do note that redder bands are generally favored by most, but not all of our science cases, we do stress that U-band observations are still important for TDEs, young stellar object, and a range of science, including the measurement of metallicity. So there is a balance to be struck there. Next slide, please. We recognize that there are also tensions between different TVS science cases when it comes to sequential images taken on the same night. There are good arguments for both them being in the same filter and in different filters. And this also depends on the sky region to some extent. So we encourage the committee to explore optimizations in different regions of the sky. And of all of the intervals between visits that were considered, TVS has several science cases that benefit from short intervals, for example, fast transients and microlensing anomalies and others. That said, longer intervals are still valuable for most science cases, and we still have some work to do to evaluate the impact of that. Next slide, please. So we note that the SCOC has recommended further investigation into the Presto color strategy as proposed by Federica and her team, and we endorse that. As a recap, that strategy requested 3 observations per night in 2 filters with specific time gaps designed to characterize Kilo Nove. And that's been implemented as a metric, but the math team requested a simulation-based metric, which was implemented by Ming Lian and using the Plastic Data Challenge dataset. But the team have noticed some serious concerns about that implementation, and they wanted to stress that further work is necessary. So we want to encourage the math team to continue working with Federica and Ming during that investigation. Next slide, please. So the rolling cadence strategies are generally thought to be beneficial for TVS science, but the devil is in the details. Our particular concerns are the gaps between rolling cadence seasons, which are critical to the study of longer term phenomena such as black hole microlensing, where we could start to lose either crucial phases of the light curve or even entire transient events if the gaps are too loud. So we recommend with early coordination with other surveys here as well, to give the other programs plenty of time to accommodate Rubin's strategy within their own observing plans. And that's particularly important for the galactic bulge survey and the deep drilling fields. Next slide, please. And lastly, TVS didn't have a very strong preference regarding dithering. We do note that that astrometry is important for a lot of our science, and that will depend on making sure that the positions can be measured in such a way that they don't correlate with parallax or DCR. Next slide, please. Thanks. So in the second part of the talk, I wanted to take a few minutes to describe the recent work by TVS, which has been undertaken in response to feedback that we had from the SCOC at earlier stages. So starting with the next slide, please. To understand how we've tried to respond to the SCOC's feedback, I'd like to very briefly place it in context. In 2018, TVS contributed to approximately 40% of the survey strategy white papers, and that simply reflects the wide range of science that our members cover. Synthesizing it all into a single paper really wasn't feasible at the time. Now, all of the white paper authors were encouraged to include metrics, but not all of them were able to do so at the time. And we received the feedback that the science really couldn't be considered until there were metrics available. Next slide, please. So we encouraged our members to provide metrics, and this resulted in an expanded set of metrics from the community, which were submitted at roughly the same time as the Cadence note. And I think to a large extent, the expectation in the community was then that the metrics would then be run on all OpSims, but it's become apparent that the reality is more complex than that. Now, during the PCW and other meetings, we shared this spreadsheet of 64 community-written metrics. And our intention with this spreadsheet was to indicate that firstly, the community had answered the SCOC's concern about the lack of metrics, but also it unfortunately appeared to cause a certain amount of confusion that I wanted to clear up. This spreadsheet is not from TVS alone. We have tried to gather the metrics together from all of the science collaborations into a single location so that we could see what of the overlap, if any, there was, and combine our efforts accordingly. So it's a tool to help us collaborate with the other science collaborations. However, we also recognize that the sizable number of metrics provided proved to be rather overwhelming. And for some science topics, the SCOC received multiple cadence notes and metrics written independently for the same science topic, which then presented them with the dilemma of which metrics they should use and what configuration and so on. Next slide, please. So in response to this, we've been trying to organize the community to condense this great long list of metrics into a smaller set of figures of merit that can be used to optimize survey strategy for very broad areas of science. And we've been referring to these as metric packages. In the process, we've been reaching out to the other science collaborations to try and build consensus within each science topic on which metrics we recommend for that science area, hoping to clear up some of the mixed messages that the SCOC was receiving from the Cadence notes. And as you can imagine, that's been a major challenge. Each one of these topics is extremely broad, but we're hopeful that we can get broad community consensus for a finite set of metric packages that will then help the SCOC to evaluate the OpSIMs. Next slide, please. In order for the community to help with that evaluation and provide advice to the project, each metric package is intended to have 1 or 2 figures of merit, which the SCOC can use for high-level evaluations, plus a small set of metrics which are recommended by the science community in question. And we're working with the math team to get those integrated into Rubin Sim. The expectation is that both the figures of merit and the recommended metrics would be run over all sims by the math team. And then the science collaborations would expect to help to evaluate the metric output. I don't have time to go through each package right now, so I will draw your attention to the resource slide at the end of this slide deck, where I provided links to more information. Next slide, please. I also wanted to briefly note that many of our members are working on contributing papers to the special edition in APJ for LSST survey strategy. As you can see from the list, a few papers have already been submitted and a number are in preparation, but we've encouraged our members to make sure that their metric code is integrated first and before the end of the year. Next slide, please. Now, to wrap up, Zeljko specifically asked which questions or concerns we have that have not already been discussed. So I wanted to finish by highlighting some areas of concern. We'd like to understand what scope that there will be for incorporating higher cadence intensive observations, such as those proposed for star-forming regions. We'd also like to understand the process for declaring and executing targets of opportunity with Rubin. Who will decide this and on what criteria, etc. That will enable the community to coordinate follow-up for a lot of different science, for example, gravitational wave alerts. And we look forward to the session later on in the workshop on that topic. We note that a lot of transient science is in particular does depend on obtaining template images and other observations in the early phases of LSST. So we are interested to know how this is being coordinated with the needs of commissioning. And related to that, we would like to know whether the metrics that have been recommended in the TBS commissioning note should be integrating with the math at this time, or are those considered to be separate? In some cases, we note that the metrics that are recommended for commissioning are actually the same as those recommended for microsurveys, but microsurveys are being considered later. So finding out what the timescale is for that would be appreciated. And lastly, I mentioned that the community are trying to rationalize the metrics that we've presented to the math team and work with the team to integrate with them. If by the end of this year, there are community recommended metrics that have not yet been integrated or which will not be used for whatever reason, we'd like to recommend that the authors receive feedback on why that was the case. And I will stop there for questions. There's one more slide, which is the resource slide that I mentioned earlier, and there's a lot more information on what we're currently working on and specific metrics there. Thank you very much.
Thank you, Rachel. Questions? I see, oh no, that's, Bill is happy with your presentation. I thought he wanted to ask a question. There is a hand from Meg.
Yeah, I wanted to try to understand what you mean, I guess, partly by community metric and partly by if the SCOC decides not to incorporate a metric. Or maybe I'm misinterpreting a little bit. So you've reached out to every science collaboration, solar system, AGN, et cetera, or has it only been ones that are focused on transients to make this master spreadsheet set of math metric fields of a figure of merits? And you're going to, this set is going to become the master one. Is that, well, that's the hope? And that it's up to the math team to decide if there's 3 metrics that are submitted and one's in this community one and then one's not. The math team and the SCOC will give feedback on why that metric was not run or not incorporated into the math.
No, so we've reached out to build metric packages specifically in those areas where we have a lot of overlap with other groups and where there was confusion previously. Now, I know that the math team have done a great job of integrating a lot of metrics, and in many cases there was no confusion. It's integrated, they're all good. We haven't worried about stuff that is all good. So we're really focusing on stuff that, for example, for the galactic plane, there was some confusion over microlensing, how we can merge this huge range of metrics into something more rational and try and avoid some of the duplication. So that's one area where we focused on. And the idea is then that the community will say, here's what we recommend for all of these science areas, and get a lot of people to sign up to that so that there's no ambiguity, no confusion from our side. And then if that package is not accepted for whatever technical reason or whatever personnel-based reason, then there should be some feedback on why was that the case. But the intention is that it would hopefully supersede that long confusing list that we had previously.
So are these soon to be a pull request?
Yes.
Or are these still in
Very
development? I mean, like, are they very soon, like in the next few weeks?
That's the plan, yeah. We've explicitly told people if you don't get this finished by the end of December, forget it.
Okay, thanks.
Thank you, Meg. More questions for Rachel? Bene?
Hi. So the list of metrics is that, do you consider that complete, or can we still add metrics to this idea?
You're very welcome to add more metrics. It's as complete as we could get it based on, in fact, we've been accumulating metrics from several meetings, and every meeting we've said, please add your metrics to this list. So it's as complete as people have contributed. But yes, people are still adding metrics to it, and that is very welcome. So please do.
Excellent, because yeah, I'd like to.
Excellent.
Thank you. More questions, comments? Let's see, there is lively discussion of femto surveys on chat. Will has hand up. Will, we can't hear you. You are on mute.
Thank you. Sorry, I thought it was the mask. There's a contribution from Roberto Assef of the AGN collaboration in the Slack channel. I don't know, maybe does Roberto want to, do you want to read your contribution?
Sure. I can mention a couple of words. So I'm not sure what happened, so sorry if we're not having prepared something. But so I can give you an idea of it. Basically, when the testing we ran for the Cadence nodes, we identified that there were not really many options that were critically bad for AGN science in WFD, but we did find some things that would actually optimize our science and would be quite beneficial. So one of them is we identified that the difference in depth between the different strategies being considered wasn't too important in terms of the number of quasars, but the area was. So the baseline, the larger area baseline that's being considered now, it's actually beneficial for given what we found. We also found that the only option that could actually hurt the photometric redshift aspects of things were the not changing when pairs of filters were, or pairs of observations were being done, to not actually change them. And so the baseline same filter, and that's no longer being considered. So that is also, from my point of view, beneficial, even though I should stress that we haven't really had much time to run with the new simulations, all of the metrics we have developed. And one more thing perhaps to add from the AGN point of view is from the work that Wei-Jian Yu and Gordon Richards did, which I don't know if either of them are connected, but one of the things they had identified was that it was beneficial for the structure function error. It was beneficial to have longer U-band observations. So again, the recommendation of having longer one snaps of 50 seconds should also be beneficial for AGN science.
Thank you, Roberta. So it seems we are out of questions. So we could finish early. So last call, comments, questions, not necessarily about these science collaboration feedback, possibly about earlier presentations.
Perhaps I wanted to sort of ask, but also sort of advertise that I think that the math team have made themselves available for office hours, which I think have been very useful to those of us who went, even though I only was able to go once. And so that's also a way to work with Peter and Lynne, and they're very graciously saving some of the time to directly interact with us. I want to thank them for doing that and encourage everybody to take advantage of that.
Thank you, Fed, for pointing this out. Indeed, Lynne and Peter have been working very, very hard on this. Okay, so tomorrow we'll start in session 3 with Lynne, Peter, and Eric Nielsen, who is also a member of the Cadence optimization team from Fermilab. They will describe some changes in the code base, and in particular, Eric will take you through his notebook that would teach you how to use math. So if you're interested in getting your hands dirty and doing analysis yourself, tomorrow session 3 is the place to be. Or if you have students who would you like to deploy on Cadence analysis, that will be a good jumpstart for them. And then session 4 will be community contributions, and we'll have 4 blocks that you can find on our agenda webpage. So it looks like we are done for today. We had about 80 plus people at the peak. So thank you all for dialing in. And I hope to see you all again tomorrow morning or afternoon, whatever time zone you may be in. Thank you and have a great remainder of the day.
Thank you, Zeljko.
Thank you.
Thank you. Bye.
Thank you.
Thank you, Peter and Lynne, for the talks.